We are now live and waiting for attendees to join in. Thank you for joining in. We have people coming in to the live session. We'll wait for 4 more minutes before going live. While you are here, we request you to download a free report on this topic by clicking on the link in the chat window. Here is the link to download the report. Thank you for joining in. We'll go live in next 2 minutes. Meanwhile, we request you to download the free report by clicking on the link in the chat window. We are still waiting for people to log in. We'll start in the next 2 minutes. Thank you for joining us today. Thank you for downloading the reports. We'll be now going live. Hello and welcome to this exciting webinar on the future of mobility, the self-driving vehicles and the significant role of geo-information. I am Harsha, your host for today's webinar, organized by Geospatial Media and Communications along with Geonovum. Geonovum is the NSDA Executive Committee in the Netherlands, devoting its time to making governments perform better with spatial data. Geospatial Media is a catalyst organization working towards creating awareness on geospatial technology by undertaking policy advocacy, connecting stakeholders and communities worldwide. Today's webinar is going to discuss the role of geospatial information in self-driving vehicles. This webinar is an outcome of a report we have recently published. Please download this free report from the link you will see in the chat window. To discuss further on this, I would like to welcome Dirk from Geonovum and my colleague Ananya, who shall bring out great insights on this topic. First, we'll have presentations, then we'll have detailed discussions after the end of the presentations. So, if you have any questions, please don't hesitate to type in your questions at any moment during the webinar. Over to you, Ananya and Dirk.
Thank you, Harsha. Good evening, everyone. On behalf of Dirk and myself, I welcome you all to this exciting webinar. Today, we are going to discuss one of the most talked about technology innovation that is going to disrupt the entire automobile industry. Yes, you guessed it right. The autonomous vehicles, or most commonly known as the self-driving vehicles. Generating immense curiosity among all stakeholders, I'm going to help you understand what the self-driving vehicles are and what their ecosystem looks like. Dirk, on the other hand, will highlight the crucial role of geospatial data and infrastructure and the decisive role the government shall play in making them successful. Let's begin. 94.7 million. Yes, that's the number of self-driving vehicles that are expected to be sold annually around the world by 2035. How incredible is that? A technology that was only part of science fiction till now going to become a happy reality. Popularly coined as vehicles of the future, the self-driving cars are moving in a forward direction, encompassing innovations from the digital, automobile, geospatial, and all other ecosystems, disrupting the entire transport industry. We are all well aware that traditional automobile companies like Audi, BMW, Toyota, Lexus have already stepped into the domain by offering self-driving capabilities to their cars. Simultaneously, technology giants such as Google and Apple too have entered the smart car market, bringing in new technologies and new services along with increasing investments so as to push the autonomous technology to the limit. But before we dive into the technology aspect of it, it is important to understand what the self-driving vehicles actually are. Of course, the name self-driving vehicles is self-explanatory. One may think that no further introduction is needed. But there is more to it. As defined by the National Highway Safety Administration, these vehicles can drive themselves without any human supervision or input to control the steering, acceleration, and braking. This means that the technology imbibed in these cars enables the car to go from point A to point B without any human on board. Is it not a disruption that is unprecedented in both magnitude and scope? This does not mean that autonomy is yet to come. Autonomous features are already in most of the current set of wheels. Self-park steering, adaptive cruise control, and lane steering are few of the foundational autonomous features that are already present in most of the cars today. In the next few slides, I'll quickly take you through the 5 levels of automation and then cite some examples for the same. At level 0 or no automation level, the driver is entirely responsible for the vehicle and its control system at all times. At level 1 or the function-specific automation, 1 or 2 functions are automated. For instance, at this level, the automation feature will mostly be to provide electronic stability and brake assistance. At level 2 or the combined function automation, 2 primary control functions are automated together. As we will see in the examples, this could mean enabling the adaptive cruise control in combination with lane steering. At level 3 or at limited self-driving automation, vehicles will have full control of all safety critical functions. The driver will be needed for occasional control but with sufficiently comfortable transition time. At level 4, at which full autonomy is achieved, the vehicles is designed to perform all functions of driving by itself. There will be no need for a driver to control the vehicle. Now let us brush through some examples. The 2016 BMW 750i xDrive has a driving aid system called the Driver Assistance Plus and the Active Driving Assistance Plus. The car also has a nervous system of 1 stereo camera and 5 radar sensors. A stereo camera gives the BMW depth perception to identify pedestrians and lane markings. 5 radar units, including one in the lower grille, monitors traffic from every direction. The 2015 Infiniti Q50S has the intelligent cruise control, predictive forward collision warning, forward emergency braking, lane departure warning, and active lane control. The nervous system in the car is composed of 1 camera and 1 radar sensor. The windshield camera provides vision for lane control, while others operate the rain sensing wipers and automatic high beam control. Radar at the left side enables adaptive cruise control. In the 2015 Tesla Model S P85D, the windshield camera and the radar sensors gives the Model S a 20/20 vision. The ultrasonic sensors check for a clear path to the side before enabling a lane change. All Tesla vehicles have the hardware needed for full self-driving capability. 8 surrounded cameras provide 360-degree visibility around the car with 12 updated ultrasonic sensors and a forward-facing radar which enhance the processing capabilities in the car. Now let us look at some of the innovations and investments which are defining the direction of the self-driving vehicles industry. Ford has invested $1 billion in an artificial intelligence startup with the intention of having a fully autonomous Level 4 capable vehicle for the commercial market by 2024. General Motors has started testing self-driving Bolt electric vehicles on some public streets in California, Arizona, and Michigan after buying the autonomous tech startup Cruise Automation for $1 billion. Toyota is partnering with Stanford University and MIT to research artificial intelligence and robotics in order to bring greater autonomy to Toyota cars by contributing $50 million over 5 years. NVIDIA is focusing on putting a lot of compute horsepower in the vehicle itself so that the vehicle can drive without needing to be connected to the network constantly. Audi is adopting NVIDIA's drive computing platform to accelerate the introduction of next-generation automated vehicles for greater driving safety and new mobility services. Honda has unveiled a new self-driving concept called the Cooperative Mobility Ecosystem that will ensure vehicle-to-vehicle communication in connected cars and smart city infrastructure, reducing traffic congestion and improving road safety. The Cooperative Mobility Ecosystem aims to connect the power of artificial intelligence, robotics, and big data. Looking at these investments and the exponential rise in innovations, it is no surprise that the industry estimates that by 2020, the autonomous vehicle market will be worth $87 billion. Let us now discuss briefly on the potential benefits and risks and challenges associated with autonomous vehicles. Few of the benefits of the self-driving vehicles are increased independent mobility, reduced accident risks, abundant platooning, fuel efficiency, improved land use, additional job creation. Where there are benefits, there are challenges as well. Some of the common risks and challenges associated with self-driving vehicles are software failures, information hacking, loss of employment, privacy, safety concerns. Now that we have defined what the self-driving vehicles are, let us discuss the ecosystem for the same. Defining the ecosystem for the self-driving vehicles has always been difficult. However, as the penetration of autonomous vehicles is accelerating, the ecosystem is beginning to get established. The past 1 year has highlighted that as various milestones of autonomy come into focus, there begins a growing interest of new stakeholders in the driverless car ecosystem. As these stakeholders get defined, it becomes imperative to determine the action points for them. In the next few slides, we shall attempt to define the role and responsibilities for few of the stakeholders of the ecosystem. Fasten your seatbelts, you are in for a ride. Starting with, software companies are going to be responsible for providing the right framework for the proper functioning of autonomous vehicles. The role of the technology and the software provider is to boost software reliability and cybersecurity and to establish communications between vehicles and internet-enabled devices. Deep learning and artificial intelligence will be important because they involve algorithms which are more accurate at object recognitions, thus improving perception, reducing power consumption, and enabling identification and prediction of actions. These systems will also play an important role in manufacturing product lines and crash tests by reducing time and cost. Self-driving vehicles are going to require a standard vehicle technical infrastructure, which will need to be developed by the original equipment manufacturers. For this, the OEMs need to start investing and acquiring the right technology expertise and consolidate ventures that integrate hardware and software systems for the efficient functioning of autonomous vehicles. The government, however, will play a primary role in this ecosystem. They play a defining role in the establishment of an enabling and protective legal framework and in establishing open, interoperable, and internationally oriented data policy and governance. Also, the government and the transport providers are together going to be responsible for maintaining the quality of public infrastructure, a necessity for autonomous vehicles to run smoothly. Geospatial content providers have a major role to play in the ecosystem, for they will be responsible for providing continuous stream of location and situational awareness data. The data needs to be of high resolution, real, accurate, and authenticated. Finally, one of the most interesting players in the driverless ecosystem are going to be the finance service providers, for they are going to reshape the ownership models and introduce new revenue streams. The traditional vehicle ownership models are going to be transformed, thus altering the nature of car financing. Profound changes are also expected in insurance models available. Insurance companies in United States have already begun to evaluate the need. Now that we have established the action points for the self-driving vehicles ecosystem, please join me in welcoming Dirk, who will present in detail about the geospatial component of self-driving vehicles and the role of the government in its success.
Welcome to the second half of the presentation. I'm Dirk-Jan Venema. I work at Geonovum in the Netherlands, and I will be presenting the second half. We've heard about the basics of self-driving cars, the direction and trends, and the self-driving vehicle ecosystem. Now we will dive further into geospatial and self-driving cars, some of the technologies found inside the vehicles, and the possible role of the government. I will try to include more background information, go beyond the publication at some points, and provide further examples. Geographic information and autonomous vehicles. Since 2009, when Google started their autonomous vehicles project, the self-driving vehicle industry has been growing at an accelerating rate. And the geospatial industry has played a crucial role in this emerging technology that relies heavily on geographic data. This is due to some advances made in navigation and positioning technologies. So the self-driving vehicle industry is largely based on such sensors, and some of these are geospatial, such as LiDAR, radar, or navigation. The self-driving vehicle requires information about its environment, and it consumes data such as maps, but it also produces data via sensors. And the data is the oil of the autonomous vehicle. It is at the center of the functioning of self-driving vehicles, and without this data, no driverless car could work. So there are various sensors in the car producing this data. They consume a lot of real-time data for efficient driving. And the number of sensors is continuously increasing because of their proved benefits represented in avoiding accidents or higher driver efficiencies. These benefits are not limited to the vehicle's driver, but they're also relevant to other vehicles and third parties. So all these sensors essentially make the autonomous vehicle act as a mobile supersensor, producing vast amounts of data. And therefrom comes the concept of a vehicle as a mobile sensor or a vehicle as a resource. For example, the driverless car of Google is capable of producing 2 petabytes of data a year, which is 0.75 gigabytes data per second. And by 2020, an average autonomous car may be able to process 4 terabytes of data. So there's 3 important notes to be made here. First, the vehicles have no power constraint because they have a large energy supply, which is useful for the various sensors installed on the autonomous vehicle. Further, there's a powerful processing capabilities in autonomous vehicles, and there's enough room for sufficient data storage units. Here we see the 5 main categories of automotive electronics. They contain some of the most important sensor technologies in modern cars today. So currently, most vehicles have 60 up to 200 sensors in the car already. They measure a variety of things. Could be engine emission controls, engine performance, backup assistance, or onboard diagnostics. Generally, when we talk about autonomous vehicles, we tend to focus on the advanced driver assistance systems. And on the next slide, you can see that many of these modern sensors in the advanced driver assistance systems, they have a long history in the car manufacturing. For example, radar has already been used for radar-controlled cruise control. The ultrasonic, of course, for the backup assistance, and infrared, so the night vision, has been used for body heat detection, for example in police cars, and of course the GPS, the positioning and navigation systems. When we think of sensors in autonomous vehicles, we generally speak of the sensors we can see on the slide. So GPS used for location and positioning, such as GPS, Galileo, GLONASS or the Beidou 2. The inertial measurement unit, which is a gyroscope with accelerometers, also used for location, especially when the GPS cannot retrieve a signal. For example, in a tunnel. The LiDAR, which is useful for 3D mapping. It determines the distance of objects and the reflectivity of the objects. Then the radar, which is useful for detecting movement and the speed of objects. The camera, also for distance if there's multiple cameras installed. And of course classification to differentiate trees from the air and from the road. Then there's the processing unit, which is the core component in autonomous vehicles. And another important part is the CAN bus. So the CAN bus is a controller area network. It's a vehicle bus standard designed to allow electronic devices to communicate with each other. It allows for near real-time management of most of the sensors and the electronic devices embedded in the car. Examples, of course, are the onboard diagnostics, the airbag control, anti-lock braking or the traction control. Next is a key component of the autonomous vehicles technology, which is sensor fusion. Sensor fusion is the combining of sensory data in such a way that the end result is better than would be possible by these sensors individually. So the car that needs a wider range of sensors to fully understand its environment. And some sensors are good at certain things, whilst others are not. So the ultrasonic, for example, is good at judging distance, but only at a short range. The radar can also measure distance at a longer range and regardless of the weather, but it has a low resolution. The LiDAR is also a distance measurement sensor. It has a much higher resolution, but it loses sight at heavy snow and rain. The camera, at least if there's multiple cameras installed, is also a measurement distance sensor. And it's also good at classification, but it's not great at bad weather, and it doesn't work during the night. So by combining all these distance sensors, they could complement each other during various situations so that the vehicle can understand its environment better. Additionally, there are already sensors in the car communicating over the CAN bus, as previously mentioned, and these can also be fused together with the newer sensor technologies, as we've discussed. Next, a few examples of sensor fusion that we see in modern cars today. Firstly, the rear view camera plus the ultrasonic sensor. So the camera gives the driver a rear view, and the ultrasonic measures the object's distance, and by combining these two you get parking assistance. Next is the front camera plus the front radar. So the radar measures distance and speed of moving objects, and the camera is able to differentiate objects. So we can differentiate pedestrians from cyclists and from other cars. Then the camera plus the accelerometer in the IMU, which is used for pothole detection. A front view camera can detect the size while approaching the pothole, and then the accelerometer detects the vibration when the car hits the pothole, and then adjusts the shockers accordingly. Another example of sensor fusion is the real-time traffic data. So recently we saw that the mapping expert here has launched a real-time traffic service that pulls aggregated data from sensors in Audi, BMW and Mercedes-Benz vehicles that are driving on the roads. So these sensors are combined, so they're fused together and are useful for a variety of things. It's a traffic safety warning, so when there's incidents on the road further ahead, they can be communicated to cars further down the road. It's useful for mapping the air pollution and adjusting traffic accordingly. It's for crisis management when there's maybe a fire truck or an ambulance. And of course for urban commuting, so that commuters can pick the most convenient option based on the real-time traffic data. Next, another example of sensor fusion. So recently I read a report on autonomous vehicles and roundabouts. Currently it's not yet possible for the autonomous vehicle to detect all relevant elements with just onboard sensors. There are several reasons for this. Could be because the algorithm is computationally expensive for real-time implementation. Could be because sensors are not accurate enough. Either way, when the sensor data is fused with a highly detailed geographical map, the roundabout was accurately calculated up to 20 centimeters. Therefore, a priori map was required to obtain information about the environment, as they could not be fully perceived by the sensor-based methods. Interestingly, this leads to possible discrepancies between the high-definition map and the sensor data, because the sensor data could measure something different from the high-definition map, and accordingly there needs to be some sort of map verification via the sensors so that they could complement the HD maps. So a vehicle as a data producer or as a resource has various benefits, but it also has various challenges. For example, privacy. A lot of information will be sensed of people in public space, but also on the driver themselves, such as driving behavior. So there needs to be some mechanisms in place to deal with the privacy. Next, as we've seen in the previous slide, is the verification and the validation techniques for assuring the data quality of the sensors. Also redundancies. There might be various sensors that acquire similar data, or the same sensor acquiring data on the same object on slightly different time intervals. In both cases, this leads to a lot of redundant information that needs to be filtered out. Of course, there also needs to be an incentive for the data owners to offer their resources to others, to third parties, so that they can create sensing-based services. Next slide is geographic information, the data. So there's 4 types of data. We've discussed the in-car sensor data already, the data that's being collected by the autonomous vehicles. We've shortly discussed the base maps used for navigation and positioning. And the other two are the vehicle to infrastructure data, which is an integrated data network between vehicles or between the vehicle and the roadside infrastructure, such as traffic signals or roadway sensors. This would also include vehicle to pedestrian or vehicle to network. The fourth data is the commercial data sets, which means that autonomous vehicle data could be linked to social media, used for location-based marketing, or linked to weather data to improve the traffic safety. So next I would like to provide an example of the vehicle to infrastructure and the road and traffic signal management. So in the Netherlands currently there's two standards being adopted. There are smart traffic lights being developed and placed on intersections across the Netherlands, and the idea is that they will provide a map and SPAT message to approaching vehicles. So the map message is going to send the topology of the intersection to the autonomous vehicle, and then the SPAT message, which is the signal phase and time, it functions to inform the driver of the current status of the traffic light ahead, as well as the next signal stage change that will occur in the current path. So they are both concerned with communication between the traffic signal controller and the approaching vehicles. They provide the driver with information about residual signal time and the topology of the approaching intersection. So the base map is one of the data types, specifically an HD map. So the base map is at the center of the self-driving vehicle for efficient and easy navigation, because the sensors cannot detect everything real time, as we've seen with the roundabouts. A priori map or information is necessary to evaluate what exists, as sensors cannot detect everything. So the picture shows a map complemented with sensor data, with LiDAR and imagery. For self-driving vehicles, it's crucial that these maps are of high precision, highly accurate, and are updated frequently. So the maps, they usually have three components in them. Firstly, there's the physical layer. It's the physical dimension of the lanes, their shape, their width. Secondly, the map contains a database of interesting objects. Could be traffic signals, sidewalks, intersections to spot pedestrians, because it's of course much easier to decode these pedestrians if you already know where they might be in advance. And thirdly, there's textures, objects, and edges which the car uses to figure out exactly where it is on the map. Self-driving vehicles, they need a unique and detailed mapping system so that the data is accessible to all stakeholders in the self-driving vehicle ecosystem as easily as possible. On the slide you can see three types of infrastructure that are relevant to the self-driving vehicles. First, there's the Global Navigation Satellite System, which is a constellation of satellites that provides the position with the global coverage. The advantages of having a GNSS are accuracy, redundancy, and the availability at all times. And location is of course at the core of the data. Next, the data infrastructure. So the self-driving vehicles are gathering a lot of real-time data with the sensors that can range from traffic patterns, traffic flows, to delivery tracking. This data is continuously gathered and will need a central repository for storage and further distribution to other parties in the self-driving ecosystem. This data needs to be reliable, therefore needs to be verified, validated, authenticated, and generally standards are used for this. And thirdly, there's the communication infrastructure. The self-driving vehicles will need a steady communication network to communicate with the infrastructure, other vehicles, and the network for more efficient and safer traffic flows. Self-driving vehicles are, of course, not bound to administrative borders, and therefore data amongst regions and countries ought to be aligned. So the geospatial intelligence of the driverless vehicles will rely heavily on a well-established geospatial data infrastructure, and not just in a single country, but even beyond administrative borders. So if the autonomous vehicles are becoming a reality, setting data standards and defining a structure is important. And these standards, they need to be available in a format that can be used by the autonomous vehicles, but it's also easy to interpret it. And while setting data unification standards, it is important to consider the standards laid down by established standard development organizations. And there are already many organizations working on standards for various elements in the ITS, which is the Intelligent Transportation System landscape, as you can see on the screen. And as autonomous technology comes to the forefront, it's crucial for the government to get involved as well, so they can analyze and address issues of standards and structure of the data to be used. This could be related to creating open standards, interoperable standards, policy standards, and technical standards. And these all need to be defined beforehand, so that the data is available in a uniform format and structure, which will benefit the autonomous vehicles far more than the risk and costs associated with it. The government too has a significant role to play in setting up standards and structure for geo-information. So the self-driving vehicle has a great potential and can yield a wide array of benefits. However, cashing in on those will require a framework that involves the government. So the government, they could establish and enable a protective legal framework and establish an open and interoperable data policy. So first, the protective legal framework. There's 4 issues at hand. First, there's safety, which is related to data safety standards. So is the data properly encrypted? Could be metadata on vehicle. So who is the manufacturer and who does the car belong to? But it could also be road and traffic signal management for safer traffic flows. Next, there's the privacy and the data sharing. This is related to the right to not be followed and who owns the data. Thirdly, there's liability. Who is responsible? Which is a question often raised at insurance companies. How do you divide the blame between a human driver and a car's automated system? And lastly, there's cybersecurity and the vulnerability to hacking and the proper data encryption. So for all these issues, there need to be a legal framework, there need to be standards and a structure to deal with these issues. So next, I would like to talk about cybersecurity. Generally, when we think of this, we think about hacking. And here's an example of hackers that took control of the car. They were able to retrieve information such as location and speed and other private information. And they were also able to control the radio, the air conditioning, the fans, the engine, the steering under certain conditions, and the brake. And accordingly, they were able to disable the brakes so that the car would drive into a ditch. Next, there's another example of cybersecurity. So in Korea, at an institute, they made an object that was emitting strong light of the same wavelength as the LiDAR. They were sending their own laser pulse directly to the LiDAR. And in that attempt, they were able to make their object invisible to the LiDAR. This could, of course, be quite dangerous for autonomous vehicles when they would not be able to see the objects. Next, another example is done by an artist in Great Britain. He created what he called magic salt circles or road markings. So he created a straight line and a dashed line. And according to the autonomous vehicle software, a dashed line means you can pass and a straight line means you cannot. Therefore, it was trapped inside the circle. Governments could establish and enable an open and interoperable data policy. In that policy, data must be available, accessible, and reusable. And it is imperative that standard policies are formulated for both standards as structure to create a predictable and inclusive ecosystem. In that attempt, it is important to appreciate the international context and use standards that have already been created by the large standard development organizations. The geospatial community could play a crucial role because location data is the linking pin between various types of data. The geospatial community could pull together industry leaders and policymakers and infrastructure holders. It could connect to neighboring communities like the ITS and the IoT. So to conclude, the data is key to self-driving vehicles, location is key to self-driving vehicles, and the geospatial community could play a crucial role in unlocking the potential of the self-driving car.
Thank you, Ananya and Dirk, for this interesting presentation today on the whole ecosystem, the industry, and the relationship with the geospatial industry as well. So we have questions coming up from our audience, and the first question is on the role of space technology in driverless cars. Dirk, if you would like to answer this question.
Sure. So space technology, it's been influential to self-driving vehicles, as is the case with other domains as well. So space technology can tackle one of the biggest problems in autonomous vehicles, which is the moment of deciding the right moment to hand over control to the humans. So we've also seen that NASA has been working on various algorithms in the past for navigation and movement through space and onboard flight computing. These are all algorithms and initiatives that could be useful to autonomous vehicles as well. And for the past couple of years, NASA has been working together with Nissan to develop some of these technologies further to use in future consumer vehicles and also space exploration missions. So what I also find interesting is that the other day I heard a researcher working at the Technical University of Twente who used to work for NASA Robotics, and now he's working on robotics in medicine. And he said that the core in robotics is the same because failure is not an option. And I think that's true for autonomous vehicles as well, because people will expect the autonomous vehicles to be safe, and it cannot fail. That will not be socially acceptable. We've seen that with Tesla's first accident as well. So I think that approach and the mindset that NASA has is also important for autonomous vehicles. And one more thing is that there's also, of course, other sectors that have useful technology. For example, John Deere, the tractor manufacturer, they've been working on autonomous vehicles since 1990. They wanted to build a tractor that could drive down a field, make a turn, prepare the soil, plant seeds, and harvest on its own. And they found out after 25 years that it's quite difficult to use sensors to replicate a human, and even in a controlled environment such as an agricultural field. So they still need humans to oversee and to make the final decision. So yes, space technology is quite important, but there's also, of course, other domains. Yes.
Thank you, Dirk. Thanks for answering that question. Then we move on to the next question, like this for Ananya. The question is, you have listed few stakeholders of the driverless car ecosystem. Are they the only ones, or are there any more working in this area?
Thank you, Harsha. Of course, there are more stakeholders in the driverless car ecosystem. The ones that I've listed are the ones that are actually crucial to the working of the driverless car ecosystem at present. The other stakeholders of the ecosystem could be the cybersecurity players who are going to be responsible for the safety and security of the driverless cars. The energy companies are going to be another important players who are going to be responsible for designing the in-road innovative charging systems. They will be responsible for working on alternative sources of energy to generate power. There could be mobile service providers as well who are going to be responsible for building new capacities and products and services which are going to help the driverless car ecosystem. Out of all these, I think the one that I should have mentioned should have been the roadway contractors who are going to be responsible for developing the smart road infrastructure, which I think are going to be crucial in the driverless car ecosystem. This may involve that they will have to work on a special metal mesh road that driverless vehicle sensors can navigate through. And I think one of our attendees asked this question if there's going to be a legal framework that's going to be needed for the roadway contractors. I think so, yes. To develop a road system which will be feasible for the autonomous vehicles to drive on, you need a legal framework. So I guess that should also be developed. And apart from that, the ecosystem, like I mentioned, is still in the establishment phase. So it's going to take its own time. It's still developing. It's going to develop more as and when we reach the time when driverless cars are going to become a reality.
Thank you, Ananya, for answering that question. We'll move on to the next question on how important is the policy and legal framework for autonomous cars. And I request if Dirk can take up this question.
Sure. So I would actually also like to comment on the question about the privacy concerns. I think it's also related to this question. So first, about the privacy concerns and self-driving vehicles. Well, sure, there's a lot of privacy concerns. There's many ways to tackle it. I think there's two I could mention now. There's something called privacy by design, which means that there's algorithms close to the sensor that essentially, for example, an imagery sensor, that it automatically blurs faces before actually processing the data further and sending it to external parties. So that's called privacy by design. You could look that up. And I think also that a lot of the data will be handled in the car itself before actually sending it to other parties. Could be first verified and validated, perhaps aggregated and further anonymized. And then the legal framework. So as I've said, that's going to be quite important. For example, legally speaking, there's quite a few limitations. So in the 1968 Vienna Convention on Road Traffic, to which 37 countries are parties, it actually specifies that a vehicle requires a driver to be able to control his vehicle at all times, so as to be able to exercise due proper care and at all times to be in a position to perform all maneuvers. So before it's even possible to perform experiments, you already need to adjust the legislation. So that's the reason why the legal framework is important, because right now it would not be possible to legally drive an autonomous vehicle on the road except for certain experimental areas. And you see that in various states, of course, in the United States, in European countries as well, that they're working on legislation to make the experiments possible. And eventually, this legislation needs to be, we need to be brought to a mature level. So regarding privacy, liability, security, all those things, to make autonomous vehicles possible in the future.
Okay. There is an additional question on this, Dirk, like how about legal framework for road infrastructure or road authorities? What's your take on that?
So what was it? Road authorities and road infrastructure. So I think it's safe to say that if autonomous vehicles are going to become a reality, the road is going to change, and probably road authorities will have a different role to play. So accordingly, the legal framework will have to adjust to complement the autonomous vehicle. And how exactly it's going to change, personally, I wouldn't really know. I think you would have to ask that to road authorities.
Do you see some kind of developments happening on these lines in Netherlands or in Europe elsewhere? In your knowledge, Dirk?
Well, in the Netherlands, there's a few large initiatives. One of the most important ones is talking traffic, of course. They want to, well, there's something called ITS, so the Intelligent Transportation Systems, and they want to make that a reality. So they are exploring a lot of issues with, for example, road authorities, with road infrastructure, how that's going to change to well, experiment the autonomous vehicles. And what you see, for example, in road infrastructure is that on intersections, which is quite problematic for autonomous vehicles, is that these vehicles, they need to connect and communicate with the infrastructure and also with other vehicles. So what they're doing, like I've said in the presentation, is that there's the infrastructure changes so that the traffic lights, they become intelligent, as they say, so that they're able to communicate their status to the vehicles that are approaching. So that's an example of how the road infrastructure is changing. And another one is there was a platooning challenge in Europe to, of course, one of the problems with autonomous vehicles is that data is often different in various countries or various regions. So the platooning challenge in Europe, it was a test to see if a platoon of trucks could move through some countries in Europe to the Netherlands. So they had to adjust a lot of legislation, a lot of legal issues. They had to adjust data, harmonize data to make it possible that these trucks would move through Europe. So that's another example of some experiments that were done here.
Okay, thank you, Dirk. We have one final question before we wrap up. The question is about a role of SMEs in the GIS industry. How will they play a lead role in this ecosystem? If you want to answer, any of you want to answer?
So I think SMEs, so that's the small and medium-sized companies.
Yes.
So what is the role of SME companies with local presence in GIS? Well, I think that's a very broad question, of course. Generally, I think most SME companies, they at least in the Netherlands, they have quite a role to play. So you see maybe that they develop some location-based services that could complement the autonomous vehicles. I suppose they often make sort of, let's say that the government usually, or at least it's thought that they should create the framework, let's say the basis, and that maybe SME companies, they can create additional opportunities or services that rely on that infrastructure. But very specific roles that they could play, yeah, I think it's difficult. It varies a lot. They have roles in every process, I think, in the autonomous vehicle industry.
Okay, thanks for that. Thank you everyone for joining this webinar today. We are winding up the webinar now. The recording for this webinar will also be available and will be sent to your email inbox. If you have any further questions, you can always reach us. And thanks one and all.